and transitions for events. And current state is designated by a marking, which puts some finite number of tokens, maybe 0 into each place. And so this is an example, and a firing rule is as follows. So just if we have a transition T here, and we have two input places, H2 and O2, and then so just one output places. And arc labels designate the number of tokens needed for transition firing. So this transition firing, so the T may fire or is enabled if we have at least 2 tokens in H2 and 1 token in O2. And after firing, it consumes the corresponding number of tokens from input places and puts so just here 2 tokens into output place. So that's a firing rule, and the general behavior is so just for each state, for each marking, we just can look which transitions are enabled, and then we choose non-deterministically transition to fire. So what is important with Petri net that we can do formal analysis of behavioral properties. So we can prove properties. That is very important. So it is a formal mathematical model. And concerning properties, so just usually they are divided into 2 classes. These are behavioral properties and structural properties. So behavioral properties are those properties that depend on initial marking, and actually they are based on constructing the reachability tree or reachability graph for our system. And structural properties are based on analysis of the graph structure. So then, of course, they are much more effective. So concerning behavioral properties, of course, that's reachability, boundedness. That means that in each reachable state, the number of tokens in each place is bounded by some natural number. Coverability, so just it is a special thing for Petri nets, not only for Petri nets, but the point is that Petri nets have some monotonicity property. That means that, so just it is easy to know that if a transition can fire in some marking, then it can also fire in a bigger marking. What is a bigger marking? A marking which have at least the same number of tokens in each place. Because so firing of transition depends, I can return here. So if T can fire, so it needs 2 tokens in H2 and 1 in O2. Of course, if our marking is bigger, that means that so just it have more or the same number of tokens in each place, then the transition also can fire. And we have, and also the output will be not less than, actually bigger than the output here. And with this monotonicity property, so just we have some special kind of properties connected with coverability. So covers, bigger means covers. Yeah? So then it is much easier to answer the question not about reachability, but about coverability. So whether we can reach a marking which has at least as much tokens as a given marking. So that's the coverability property. So if I have time, I'll show you how it can be checked. and but I'm afraid I can't tell about everything. Then deadlock, freeness, liveness, fairness, all these properties are decidable. So reachability graph, it's very natural thing. So we have a Petri net, so we can designate a marking as a vector. So just if we fix some order for our places, so then M0 means one token in the first place, one token in the second place, and 0 tokens in all other places. And then, so in this marking, T1 can fire and T2 can fire, so we have 2 outgoing arcs, and we just systematically construct this reachability tree. So then the reachability problem is to answer the question whether for a given initial marking and given target marking, we can reach the target marking from the initial one. And this problem is decidable, but the complexity is very high and the algorithm is very complicated, so actually it is not used in practice, I guess. So of course we can unfold the reachability graph as far as we can or as we need, but we can't be sure that we reach the target marking. Boundedness is a property which designates that in each place we have a bounded number of tokens in all reachable states. Here in this example we have a producer on the left and consumer on the right, and we have a buffer. So producer can put an item, a token, into P3 buffer, and consumer can consume it, take it from this place. And it is clear that, so actually the number of items in our buffer is unlimited, yeah? Because so just the consumer may be lazy or very slow, and then so just the buffer, we may have an overflow. That means that this Petri net is not bounded. Of course, boundedness is important. First, it is a natural property, for instance, for this buffer. So we would like to estimate where we may have an overflow or not. And the other important thing is that when we have a bounded net, then the reachability graph is finite. So just we have more chance to get a complete analysis of the net behavior. And this property is also decidable, and it is, the algorithm is based on so-called coverability tree, and the idea is that if, so just starting from some marking, we can reach a marking which covers so just starting from M, we can reach a marking which covers M. That means that we can reach strictly covers. Then we can reach even a bigger marking and then a bigger marking, and that means that we have unbounded places. So just, I think I will not speak about this because I would like to spend time on structural properties, which may be more interesting. But this is a very interesting property, and there is a theory of well-structured transition systems, so some other systems have also this property. Safety is a special kind of boundedness, and it is one boundedness. Each place has not more than one token in all reachable states. This is important for different kinds of technical systems, and for instance, here also when we have a system with shared resource, then so just we have critical sections, so just it is not allowed in many cases that 2 processes are simultaneously in the critical section. Then we use a key here to prevent this situation. And of course, so there shouldn't be two keys simultaneously, so that not more than one token in each reachable state. Liveness is another important property for different kinds of application, and it means that, so actually there are some several ways of defining liveness, but most popular would be that for all reachable state, we can fire each transition in the future. So it is not the case that some transition will not fire at all in the future. This means that in some case, so live system should function in all its possible ways. And fairness is another important property, and it is important not only for Petri nets, but for all systems and for verification. This example is a dining philosopher. So this system illustrates dining philosopher problem. So I guess, should I tell what is it? So just, I can tell you that, I was at the lecture of Dijkstra when he was presenting this problem. That was his Novosibirsk. I was a PhD student at that time. So, well, there is a table with, usually they say spaghetti, and philosophers sitting around it, and to eat spaghetti, each philosopher needs 2 forks. And there are, so for instance, here 4 philosophers and 4 forks in between them. So that means that if one philosopher is eating, the neighbor can't do it because they share a fork. And so this system illustrates many interesting things because there could be deadlocks, and another problem is starvation. For instance, if there are 4 philosophers, then it could be that, for instance, the first and the third eat all the time, and the other 2 can't get a resource, yes? And though the system is live, its function, everything is going on, and this is called starvation. So this is not also good. And fairness means that sharing should be fair. So just it can't be that one process uses a resource and the other has no access at all to it. So about structural analysis. As I said already, it is based on analysis of the graph structure. Petri net is a bipartite graph. And then we do not need to construct the reachability tree, and of course, then we have much more effective algorithm. So also I'll speak just about invariance of Petri nets, so the most popular methods of Petri net analysis. And here, so just what is important, the Petri net is bipartite graph. This is an incidence matrix for it. And what is really nice with Petri nets, that their behavior can be described in terms of linear mapping, I would say. Yes, so just its properties can be analyzed with the help of solving linear equations. So just next slide. This is an incidence matrix, and so just what happens? We have a marking. You see this column, a vector, which designates so 1 token in the first place, 0 token in the second place, and so on. We have this incidence matrix, which actually consists of rows which characterize transitions. So just when we have a transition, you know that it consumes tokens and produces tokens. And so here, -1 designates that it takes 1 token from the first place, and +1 designates that it puts 1 token to the third place. And then, so just U here is the vector, which is called Parik vector, which says how many times each transition fires. Then, so we have this equation which describes us M prime, which is a result of firing of 1 transmission, T1, 1, T2, 0, T3, and so on. Yeah? So just the result doesn't depend on the order of firing. The possibility of firing does depend, because we should have enough tokens, and intermediate marking is important. But concerning the results, we can just compute it where this. Yeah. Better look here. So you see, we have here a very small Petri net, so just easy to follow. There are just 2 places, so marking has a vector of size 2. So initial marking is 1 token in P1 and 0 in P2. Incidence metric says that T1 takes 1 token -1 in the upper left of the matrix from P1 and puts 1 token in P2. Yeah? And the second takes 1 token from P2 and puts 1 token in P1. Then U is a vector which says how many times T1 and T2 have fired. Then if we could reach, for instance, a marking with tokens both in P1 and P2, that means there should be a solution to this equation. So this is a very easy way to check non-reachability here, because this equation, it is easy to check, has no solutions. When we look at this Petri net, of course, we can see immediately that we always have either a token in P1 or a token in P2, but not simultaneously. But we can prove it formally, not only with, of course, these equations, but with equations as well, just by checking that there is no solution for this system. Proving reachability is much more complicated. But if we have a solution, it doesn't mean that the marking is reachable, because it could be that, so just we have a case when, though if, so that we do not have enough resources in intermediate markings. I'm afraid I have no example here, no. But it is easy to understand that, so just of, actually the order of transition firing is important. For instance, if just we have a line, then just to fire T2, we first should fire T1. But in this equation, they are not ordered, so we can organize it in such a way that, so though we have a solution here, we can't reach the marking. So that's about presenting the behavior of Petri nets with such linear transformers, I would say. And that's why also Petri net has another name. They are also known as vector addition systems. So just in United States, they usually do not speak about Petri nets, they speak about vector addition systems, which is an algebraic structure with such rules. It is just the same. One more thing I would like to show you are place invariant, which are also very nice. And this is, they can be computed also the solution of linear equation systems, and they allow us to prove properties of Petri nets without constructing reachability. So what is the place invariant? Also, I maybe switch to example. Oh, yeah, this is a nice example. You see, this is a Petri net describing well-known process. So we have men, we have women, and we have transitions which correspond to marriage and divorce. Yeah? And we have also place for couples. So just for marriage, you need a man and a woman. So these are single men and women, and then you get one couple. Yeah. And if you have a couple, so after divorce, you get one woman and one woman. Yeah. So then, there is an invariant describing this behavior. So it is written here. You see, so just we may have a weighted sum, which says that one time the number of men plus the number of women plus double number of, twice double of couple. So it is invariant. So it is the same for all reachable states. How to check it? So we can look here and we see that if T1 fires, so there is a marriage, then we have -1 for men, -1 for women, and +1 for couple. So just the change is exactly if we add it to this sum, we have the same. And the same for divorce, -1, so +1 for men, +1 for woman, and -1 for couple. Yeah? So then we can, for the current initial marking, we have that the value of this weighted sum is 7. That means that it will be 7 for all reachable markings. And of course, this is a nice picture to demonstrate it, but such invariance may be really helpful for important things. Like here, you see this is a Petri net for mutual exclusion. So we have these two processes, critical section, and we would like to prove that there can't be two processes simultaneously in the critical section. That's the mutual exclusion problem. So they can't have simultaneous excess. And so if a process 1 is in a critical section, that means that we have a token in P3. And if a process 2 is in the critical section, that means that we have a token in P7. So we should prove that it can't be that we have a token in P3 and in P7 simultaneously. And then we can easily note that we have an invariant, which is shown here. So the number of tokens in P3 plus the number of tokens in P4 plus the number of tokens in P7 is invariant. It is the same for all reachable markings. How to check it? So just also to check all incident transitions, for instance. Of course, we can solve linear equation. That's nice. If we are lazy to solve linear equation, and we have guessed already the invariant, we can just look here. So you see T2 takes a token from P4 and ends to P3, so the result is the same, and so on. You see the point? Yes? And actually, it corresponds to this cycle even. So just you can sometimes visually see it. And then what do we have? So the sum of these three places is the same, and initially it is 1, so it should be 1 for all reachable states. And since it is 1, it can't be that we have a token in P3 and P7, then we should have at least 2, which can't be. So this proves that this is a correct algorithm which ensures us mutual exclusion for access to the critical section. So this is some illustration for divorce and marriage. I guess you copied. One more helpful notion is a notion of a trap in Petri net. A trap means is a subgraph, so just a set of places actually, such that whatever transition fires, it can't empty this set. So it also can be easily checked. So for instance, we look at NC2 and NC1 here. Then if a transition to say T2 takes a token from NC1, it it can fire only if there is a token in NC2 as well, but it doesn't take it. It takes and it checks, it takes and returns it simultaneously. So if T2 fires, it can't be that there is no token in NC1 and NC2. And we can check this for all transitions. So we can diminish the number of tokens, but we can't empty this subset of places. And then what do we have? We have an inequality saying that the number of tokens in these places, the sum of number of tokens, the sum of these numbers is greater than 0, strictly greater than 0. Together with place invariance, it helps us to deduce helpful properties. So here we have, for instance, a proof that we can show first. We would like to prove that we will not have tokens in P3 and P7 simultaneously, and then so we use this trap together with place invariance for proving this property. So I look at the time.
So we have 20 minutes.
5 minutes, yes? Because 15?
Yes, yes.
Ah, yes, fine. Then I think I have time also to tell a bit about coverability, which I consider interesting but didn't include in my slides. I'll do it on the blackboard. And after that, some comments on Petri net extensions. So you see that there are some techniques for analysis of the Petri structure and deducing some properties with invariance, place invariance, but
Yes, it explains. You know, I promised you 15 minutes, but we can, it's including questions. I mean, probably we should switch to questions. If you
Yeah. So just, I wanted just to show you this nice structure. And then the last slide is...
slide.
Yes, that, of course, I was speaking about classical Petri nets. What about Petri net extensions? For instance, for colored Petri nets, we have similar properties, but much more difficult to prove. That's the point. Sometimes we can unfold them, but even, for instance, for nested Petri nets, we can define place invariants and prove something with the help of place invariants. So this technique can be extended. Yeah, then maybe we have time for questions. So.